Log on, tune in, find out. Another good idea from Cambridge.
Discretizations of Kahan-Hirota-Kimura type and integrable maps.
Okay, it's a pleasure to be here. I'd like to thank the organisers for inviting me. So what I'm going to talk about today is integrable discretizations. So is it not loud enough? That's to get higher up or something.
They're on.
Oh, that's good. I don't know. Maybe, did you turn it off there?
I did turn it off.
Oh, okay. Well, then that.
Because I didn't think the audience wanted to hear the changer.
Good idea. That saves Steve some editing when it comes to the video. Okay, I've got quite a loud voice, as my flatmate was telling me last night, and I was worried that. So you could probably hear me anyway without the microphone, but I suppose it helps. Yeah. So what I'm going to talk about is discretizing integrable vector fields. So I'm just going to talk about ordinary differential equations today. And I should say this is work that I've done quite recently with Matteo Pretrera in Rome and Kim Towler, who's a graduate student of mine in Kent. However, I tick the box on discrete systems because that's one half of this conference. The other half of this conference is special functions. And I should say that if you want to have one sort of small message to take from this talk, then it's that if you want to discretize integrable systems, then it depends very sensitively on the class of functions that the solutions live in. Okay, so whether it's possible to do it or not, I would say seems to be rather, or how you do it is very sensitive to the kind of functions that your system is solved by. So what I could say is that if in the case where the solutions are, let's say, abelian functions or they're degenerations, then there are very good and effective ways of discretizing. But when they're other kinds of transcendental functions, then it's much more difficult. So there was already something transcendental in a map with a transcendental integral in Alfred's talk, and hopefully I'll show you a cute example which has got the gamma function in it. So there's some I know that the special function people hopefully will like that anyway. So first of all, I should say, well, what is so integrable discretization is about, if you're just talking about ordinary differential equations, means that you want to take a system of a vector field, and you want to produce a map or a difference equation which approximates that vector field. So in the story of integrable systems, there are really kind of two ways of doing integrable discretization. So although I'm talking about ODEs, most of the original discrete integrable systems were really partial difference equations, so discretizations of integrable PDEs. And the discretizations were usually obtained by using Darboux transformations, or you could say Darboux-Backlund transformations, because if you have an integrable system, then that normally means that you have a lax pair, so an associated linear system, and then that linear system has natural gauge transformations which produce new solutions of the same equations. So I would say the first kind of discretization which you can do, which arises in this way, is what I would call exact discretization. So if we're going to talk about a Hamiltonian system of ODEs, then what that means is you have a phase space M and a Poisson bracket, and you have some integrals which are in involution with respect to the Poisson bracket, and enough of them to satisfy the conditions of Liouville's theorem. And if you do an exact discretization, then what you produce, you want a map on the same phase space and preserving the same Poisson bracket and the same integrals. So when you discretize, then what you produce is some new set of integrals and they're going to be the same as the ones you started with. So if you're thinking about the level sets of your the Liouville tori of this system, then they're the same for the continuous system and the discrete system. And moreover, also, if you have a lax pair, so your continuous system has a lax pair. So I've called my manifold M, so I put a P for the lax pair. Then what is the discrete system? Well, it's really just realized as a gauge transformation on this lax matrix. So the map, so the discretization produces a discrete lax equation, which is just that, let's say L hat n is nL. So all you're doing in your discrete system is conjugating the same lax matrix by some matrix. So that's what I would call exact discretization. And there are lots of ways of doing that, or quite a lot is known about that. So, the name which Sklianin introduced for this was for finite dimensional Hamiltonian system was BT, but BT, so Backlund transformations, because really this is what a Backlund transformation is. What we know from integrable PDEs, a Backlund transformation is mapping solutions to solutions, and what this transformation is doing precisely is mapping a set of solutions to your differential equations encoded in L to a new set of solutions of the same differential equations encoded in L tilde. So that's what an exact discretization is. Then the second kind of discretization is not exact, but you can consider it as kind of deformation type. So if you start off with the same integrable system, the same Poisson bracket, and the same integrals, so you can sort of write that again. Then what you produce is, okay, you still want to keep the same phase space, you want to have the same dimensions and so on. When you discretize, what you get is, so I mean, typically any discretization will have some parameters, and typically when you think about finite difference, you have a natural parameter you consider is the time step, so I'm going to call that h. So when you do what I'd call a deformation type of discretization, what you produce is some deformed Poisson bracket, which depends on the time step h, and also a set of integrals. So again, I'm going to call them h hat, and they look like the original integrals plus something of order h. Okay, and if we go to the lax equation, then it's the same kind of story that we, if we start off with this continuous lax equation, well, the discrete version of the lax equation is again conjugation, but now the lax matrix depends on h. So again, we normally can take LH to be L plus order h, and the n matrix also is going to be identity plus HP plus order h squared. Okay, so that's deformation type. Okay, so what I'm going to talk about for the rest of this talk is a kind of deformation type of discretization, and well, as I said, when you discretize, what kind of system you get depends. If you start with an integrable system, then what you get depends rather sensitively on what class of functions the solutions live in. Okay, so the method that I'm going to tell you about doesn't always produce integrable discrete systems when you start from continuous integrable systems. So what I should say is that this general area of discretization for Hamiltonian systems, it has quite a long history, starting with particularly some papers of Moser and Veselov. But if you want to read about it in general, a really good place is the book by Souris, it's about 1,000 pages. I think it's a really fat book, but it's a great encyclopedia of integrable discretizations just for the ODE case. It doesn't talk really about the PDE case, but it really is pretty encyclopedic. However, what I'm telling you about today is something that kind of really annoyed Souris, because he'd produced this large book, and he thought he'd been completely encyclopedic. But then, lo and behold, Hirota and Kimura came along, and they produced a discretization of the Euler top, the Euler equations for the motion of a rigid body around a fixed point, and this their discretization, which was deformation type, didn't fit into any of the scheme that Souris was doing. I mean, in fact, the method that Souris mainly uses is based very heavily on using the Lax matrix and the R matrix, and as far as I know, the Hirota and Kimura discrete Euler top, no Lax pair is known for it so far. So it's okay. So that's sort of what I want to tell you about, is something about what this Hirota-Kimura discretization scheme is, and it's actually remarkably simple. Really, to explain it, I should say that it's actually older than Hirota and Kimura, because it first appeared in numerical analysis in some work by Kahan. So it's much easier to start off with Kahan, which is who wrote down a nice discretization of the Lotka-Volterra model, the predator-prey system in the plane. And in fact, Kahan's approach is an approach to discretizing any system, whether it's integrable or not, but it has the drawback that it only applies to quadratic vector fields. Okay, so let me start with Kahan. So the Lotka-Volterra system is just a very simple system in the plane. Okay, you can stick in an extra parameter as well, but I'm not going to worry about that. There's some scaling, but you can have a free parameter as well. And what can you say about the system? Well, okay, in biology, X is the predator. X is the prey, and Y is the predator. But it's not really a very good biological model, because what you find is that it's integrable, and that's really in mathematical population biology, integrable systems is sort of too special to be considered realistic. So how do we understand that? Well, you can write this system in Hamiltonian form. Can everybody see this corner, or is it okay? And I'm going to stick on the screen in a minute. So that's what the equations are given. They're in Hamiltonian form, where the Poisson bracket of x and y is not the standard one. It's a canonical bracket if you take the logarithm of x and the logarithm of y, and the Hamiltonian is this. Okay, and Well, one thing you should be sensitive to if you know about algebraic integrability is that the Hamiltonian of this system is not algebraic or anything nice. It's already got a logarithm in it. So this is not an algebraically integrable system. Nevertheless, if you look in the positive quadrant, the level sets of this function are very nice closed curves. And I'll show you some picture in a second. But what I should say is that if you try and integrate this system using standard numerical methods, so the standard method which appears in most packages like Maple, which I use, is the Runge-Kutta-Fehlberg fourth order, fifth order one. And if you integrate these equations with the Runge-Kutta-Fehlberg 4-5 method, then what you find is that instead of things lying on closed curves, then the orbits spiral outwards. So this is a blow up of sort of part of an orbit, sort of integrated up to time 5,000 with not a particularly small time step, about 0.1 or something as the initial time step. And what you see is that the energy, if you like, you can just calculate h. You can calculate the value of h for this integrator, and you'll see that the energy increases linearly with time. So if you carry on really for a long time, you'll see that the orbits spiral outwards. And this is a well-known problem of integrating conservative systems with just generic integration schemes. So that's what happens if you do the standard thing. So what Kahan did, he just proposed a very simple rule, and what he said is, okay, let's just when we take the system of differential equations, which has quadratic right-hand sides, what we do is we replace the derivative by just the standard forward difference. We replace the linear terms by an average, which is sort of a non-local average. It's the average on the one lattice point and the forward lattice point. And then when we take the quadratic terms, we replace them again by an average, where you can see what the replacement is, and similarly for the y equation, so exactly the same kind of replacement rule. And I can write this out formally, but you can specify Kahan's rule very, very simply. If you're given a quadratic vector field, the right-hand side will have generally a constant piece, which you just leave it as it is. It will have a linear piece, and for the linear piece, you just take the average of all the linear terms over two lattice points. And for the quadratic form, the quadratic part, well, you'll have a vector of quadratic forms, and given any quadratic form, there's a standard thing called the polarization identity from going from a quadratic form to a bilinear form and vice versa. And so actually all this thing is just the polarization. You replace the quadratic form at x by the bilinear form at x and the shifted lattice point. Okay, so that's what Kahan's method was, which was the first example he talked about was Loc-Volterra. And if you use Kahan's discretization, this is a point with again the same step size, and you see a lovely sort of picture of closed curves, which is what you would expect to see. So that's a very I mean, at least what you can't prove anything. Well, maybe if you're cleverer than me, you can, but you can't necessarily prove anything with numerics or just by looking at a picture. And I've become aware from looking at these pictures that you have to be very careful. But at least what you see qualitatively is the right picture that you should expect to see. The other thing about Kahan's rule for discretizing quadratic vector fields, which is very nice, maybe you can notice is that both sides of the equation are linear in all the upshifted variables. So that means if you want to find the upshifted variables, you just have to explicitly solve a linear system, okay? Then also you can notice at the same time that they're linear in also the original lattice point variables that you started with. So again, the inverse of the map you again explicitly get by solving a linear system. So in fact, what this method does is it replaces a quadratic vector field by a birational map, if that's in the plane. So that's, or in however many dimensions you want to work in. So it's an explicit method. Again, that's a disadvantage of most methods like Runge-Kutta, is that they're not explicit methods. They're implicit methods. So you have to then use Newton-Raphson to actually iterate. Okay, so that's Kahan's method. Now, what I want to tell you about now is what happens when you apply this method to quadratic vector fields in 3 dimensions, so some integrable systems in 3 dimensions. And then if I have a little bit of time at the end, maybe I'll also say something about whether one can extend this idea to a higher degree vector fields. So I have a very nice example, which is not integrable, but it's a cubic vector field, and it's also discretized in a natural way with a birational map. So it sort of raises the question of whether you can discretize any polynomial or rational vector field by a birational map. And I think the answer is yes. But I should also mention at this stage that a lot of this idea of discretization, this approach to discretization, is also has a precursor in the work of a physicist called Mickens. And Mickens has a nice book about not integrable discretization, about discretization. And he has a more, say, heuristic or ad hoc approach. But it's interesting to look in his book because you'll find some early examples of, from the early 90s, he's got some early examples of QRT maps, which he doesn't view from the point of view of integrability, but he sort of has the same spirit of integrability, if you like. Okay, so if I want to move on to vector fields in 3 dimensions, then I need a rubber. Where's that? Oh, it's underneath, thanks. Yeah, okay. So, oh yeah, okay, that's easy. Okay, so I don't want to teach my grandmother to suck eggs, as you say, but to get an idea of integrable systems in 3 dimensions, in R3, let's say, then it's a good idea to just tell you some things you probably know about the Euler top. So the Euler top, you can write it rather succinctly like this. So I'm going to use x for a point in R3, and I'm going to sort of switch between whether I use coordinates with indices or whether I use x, y, z, according to convenience. So hopefully you won't be fazed by that. But okay, so how does it look? Well, it's just k is just okay. Maybe I'll use the indices this time. And then so k is this quantity, and the level surfaces of this are just spheres, and then h is the thing that has the principal moments of inertia in it. Okay, so one thing you can see immediately from the form of the equations of motion is that both k and h are preserved by the motion, and well, so some of you also maybe know that you can integrate this system of differential equations explicitly in elliptic functions, and one way to see that very simply is that the level sets of these two integrals give you the intersection of two quadrics in 3 dimensions. And if you have smooth intersection of two quadrics in 3 dimensions, that's a natural way to embed an elliptic curve in 3 dimensions. So it's not surprising that you have elliptic functions here. Okay, we can also think of this, we can also write this naturally in Hamiltonian form. So we can write x dot is the Poisson bracket of x with h, and I've called h the Hamiltonian. And the Poisson bracket here is just the standard SO3 Lie Poisson bracket, so linear Poisson bracket. So you can write that explicitly like that. And K is just the Casimir for the SO3 algebra. But it's nice to actually think of that as to observe that that's dk by dxl. So that's sort of a good way to write the bracket, because this is actually just one bracket, and because we're in 3 dimensions and we've got two functions here, in fact this is a bi-Hamiltonian system. So we can also write this as, now I'm going to probably get a sign wrong, so I put I'll put a minus sign somewhere at some point. So we can also write this as the Poisson bracket with K with a different Poisson bracket, which is given by this formula. So this is really the right sort of picture to have for an integrable system in 3 dimensions. I say it's bi-Hamiltonian because it has two independent Poisson brackets, and they're also compatible with one another in the sense that any linear combination of the Poisson brackets is also a Poisson bracket. Okay, so this is the right picture to have of an integrable system in 3 dimensions, because if you have a Hamiltonian system in 3 dimensions, you specify one Poisson bracket, then generally, so the Poisson tensor obviously has to be degenerate, so you can think about finding a Casimir. At least locally you can always find a Casimir. So you fix to a symplectic leaf where the Casimir is constant, and then if you want, that gives you a flow in 2 dimensions, and then if you want it to be integrable, you need to have one other quantity. So you definitely have you need 2 quantities. And another way to think about this is also another way to get this is also that this flow is volume preserving. So I mean, you can see it's divergenceless, and in fact, if you have an invariant volume form, there's a nice trick which I learned from a paper of Quispel and co-workers, that if you have a system, say a flow or a map in n dimensions, and you have n-2 conserved quantities, then you can construct a symplectic form just from the volume form and the integral. So if you have a volume preserving flow or a volume preserving map, and you have enough integrals, then it's always symplectic. Okay, and then you still, if it's integrable, you still need one more quantity. Okay, so this is you see already here that there's this linear Poisson bracket, Lie Poisson bracket. So my collaborator Matteo was interested in understanding this Hirota-Kimura approach to discretization. So to get the discretization of this vector field, I won't bother to write it down now, but you write down these 2 equations, these three equations, which just look like, x1 dot is a constant times x2, x3, and so forth, and then you apply exactly this rule, this discretization rule, and I'll write down some other examples in a minute. So my collaborator Matteo was looking for bi-Hamiltonian systems in 3 dimensions to see what would happen in general, and there's a paper by Blazak and Wojciechowski, and another one by Gummel and Nutku, when they just consider this problem of having bi-Hamiltonian systems in 3 dimensions, And they write down a list of equations which correspond to so pairs of Lie-Poisson brackets. So if you like, pairs of three-dimensional Lie algebras which are compatible in a certain sense. Now, from reading their papers, I haven't been able to extract a clear result to say that this is a complete classification, but nevertheless, they have some examples, you can say, which are correct, and there is some recent work on classifying linear and quadratic, well, especially quadratic and Poisson brackets. So I think it's not too hard maybe to classify all these systems in 3 dimensions, but I don't believe from reading their papers that that they have really necessarily a complete list. But in any case, so in the Gumrala-Nuku story, they have pairs of Lie-Poisson brackets in R3, and let's say compatible in a certain sense. So compatible in the sense that you have a bihamiltonian pair. Now you have to be a little bit careful because when you take these Poisson brackets, you can't always just take the sum of 2 linear Poisson brackets, because sometimes there's a conformal factor. The volume form that you preserve is not the standard one, so it's not always quite as simple as the case of the Euler top. But anyway, they have a list of these systems, and so what I can tell you about is that what we first looked at was examples. So first 6 examples in their list, and all the Casimirs or Hamiltonians. So each system has a pair of conserved quantities. So all the Casimirs stroke Hamiltonians, depending on how you want to view them, are polynomial or rational functions. Okay, so obviously so what these systems are, if you look at them more carefully, they're all algebraically integrable in the sense that the solutions are given by elliptic functions or their hyperbolic or rational degenerations. So elliptic or trigonometric, let's say. So let me just write down one example. So okay, so that's one of the quadratic vector fields that appears in their list, and well, in this case, one of the algebras is just SO3, and with this Casimir, and the other algebra has the Casimir is just x times y. And if you think about this a little bit, again, here the level sets are both quadrics. So again, this one is solved in elliptic functions. Okay, so that's that's the kind of thing that Gumrala-Nuku consider. Then what we find is that if we discretize these systems according to Kahan's prescription or Hirota and Kimura's prescription, then we get some Poisson maps. so we discretize, then what we get is some maps. So I just call them DE1, DE2, and so forth. Again, these are all algebraically integrable. So but what you find is that instead of just getting Lie Poisson, so linear Lie Poisson brackets, you naturally get deformations. In fact, in general, you get cubic deformations of linear Poisson brackets. So let me just give you an example. So if we write down DE4, then I want to write down maybe the so this Casimir gives you the SO3 bracket, and what you find in the deformation is a Poisson bracket that looks like this. And so on. So I mean, there's also the other bracket, which is just a cubic deformation of the bracket that comes from this Casimir. So in general, you also get brackets which have, ratios of degree 3 polynomials, and the integrals for all these systems, or the Casimirs, if you like, again they're just defined quadrics again. So again, they're just natural deformations of the things you started with. I'm sorry, I've switched to epsilon as the deformation parameter. So h has become 2 epsilon because it kills off some factors of 2. So that's the kind of thing that you get. And so what this tells you is that, at least for these cases, you start with algebraically integrable systems, and you apply this Hirota-Kimura approach or Kahan approach, and you always get algebraically integrable things. So then it was more interesting to look at the transcendental case. So let me show you an example there, and this is where the gamma function comes into the business. So the next system is quite simple. The vector field looks like this. It has a parameter xi. Okay, and if xi is 1 or minus 1, it reduces back down to one of the original cases in this list. So if you discretize according to the standard prescription, then so again I've got epsilon going on instead of h. Then this is the map. I mean, you can see in a sense this system is upper triangular. The x part decouples, so you solve for x, which is a trivial thing, and then you can substitute back and solve the other two. So in fact, you're really just solving a system of linear equations, if you like, in cascade. So the discrete version of this system looks like this. just to show you what the map really is. So if you want to explicitly write it, you have to just solve this linear system. And if we look at the let's look at the first Poisson bracket. Then it's this algebra. Okay, and the corresponding Casimir is y divided by x to the xi. So you can see xi is just some real number, let's say. So in general, this is a transcendental integral. Okay. If you now go to the discrete case. So what? Yeah, I should have mentioned. So for all these discretizations, at least in all the first cases that we did, you can find that essentially the same volume form is preserved by the map as for the original continuous flow, and the Hamiltonians or Casimirs are just deformations of the ones that you started with. Okay. Now for this case, it's a sort of exercise. You can solve this system explicitly in terms of gamma functions. Okay. The x part is just a discrete Riccati equation, so that's simple. Then you plug that into here, and y is given by some ratios of gamma functions, and then z is given by some rather complicated sum of ratios of gamma functions. Okay, but you can really do it explicitly. In fact, I think my collaborator, actually just in this case just put it into Maple. Maple can solve things in gamma functions. And he came out with some answer, and I was very suspicious of it. But I was reassured that I could derive it by hand myself, and then I really believed it. Now, in the discrete case, you have a corresponding integral that you can find explicitly, which just depends on x and y, and the integral looks like this. So here's where you can also already see these gamma functions. So that's what the integral looks like. And if you look at the Poisson bracket, so you have an invariant volume form. If you look at the Poisson bracket that this integral gives you, then it's a deformation of this bracket, which is a one-parameter family of brackets here. So you have a two-parameter family of brackets. So xy is still 0 because it doesn't depend on z. And then, well, now I'm worrying that I'm not going to be able to fit this on this board, so I'll move on to the next one. So the Poisson bracket is just so xy 0 as before. Z with x is just looks kind of like the thing we had before in the algebraically integrable cases. It's just a cubic bracket, a cubic expression, but then the y and the z bracket has the digamma function appearing. So it's okay, so So the fact that this integral is transcendental gives you automatically this rather transcendental-looking Poisson bracket. Also, I should say that in this case, although I can explicitly solve the equations of motion, I haven't been able to explicitly, so the solution has three arbitrary parameters, as it must do. It's easy to obtain this integral from the explicit solution, but the second integral that you really want, I can only define that implicitly. I mean, there's a functional equation that you have to satisfy, and you can say that it has a solution of a certain type, but I can't write it down in any nice functions that I know about anyway. So the system is certainly exactly solvable, and implicitly there should be a second integral, but I don't know for the life of me how to write it down. So maybe to sort of conclude, make a summary of what the properties of these systems are. If we do this discretization scheme for algebraically integrable systems, then it always seems to produce algebraically integrable systems in all these cases. If we go to sort of transcendental, say transcendental integrable systems, then in two cases that we were able to deal with, we found that they were exactly solvable, and we found one transcendental integral, and the solutions in these cases were always in terms of gamma functions or digamma functions. When we went to a next example, that was a case where only two examples in the family had the Palinové property. So one parameter family of systems, of continuous systems, and two special values of the parameter gave you something with the Palinové property. And what we found was that just in those cases, we found something algebraically integrable, and in all the other cases, we say that we think the system is non-integrable, and that we contest in the sense of Rod Halberd's notion of Diophantine integrability. So we look at the map defined with rational numbers, and then we look at the heights of the sizes of the numerators and denominators of the rational numbers that you get by iterating the map. And what you find is that the logarithm height of the heights grows exponentially for these other cases. So my student Kim Towler is actually trying to understand these other cases which are more complicated. But nevertheless, the systems that you start with are Liouville integrable. You can explicitly write down quadratures for the solutions. So the discretization goes wrong. I should also say that the theory of heights is sort of well understood by the people that understand it. Let's say in algebraic geometry, in Diophantine geometry, so the heights of sequences of points on abelian varieties is known that the logarithmic heights of the multiple of a point on the abelian variety grows quadratically with n. And what's quite interesting is that these cases, although they're transcendental, I mean they're not in the sort of algebraic world. Their heights also grow linearly with n. In fact, you can prove that they grow polynomially directly from the equations, but they actually, numerically at least, they just grow linearly. So it sort of suggests that they're not quite algebraic, but they're very close to being algebraic. Okay. So I think Rod told me to finish more or less now, but yeah, I was just going to say one more thing. So what I'm saying, this discretization scheme is enormously special because it only applies to quadratic vector fields, and quadratic vector fields is a tiny speck in the world of all differential equations. Well, nevertheless, they're very useful in applications. So all these things in population biology and chemistry, when you do what's called the law of mass action, you always get quadratic vector fields. So actually the people doing numerical analysis and applications are starting to use this discretization scheme. And what you find is that it's very robust in terms of preserving the stability properties of the solutions for non-integrable systems. So what I'd like to show you is a discretization of a cubic vector field that I obtained by the same sort of approach, but by requiring that the discretization should be a birational map. And that actually gave me a unique solution. There were two possible maps that it could be that were uniquely determined by the cubic vector field. And one of these, there was one map, and then the other map turned out to be essentially its inverse up to switching the sign of the step. So this is a system which describes a trimolecular reaction. It's not an integrable system, but it has a limit cycle. And if you integrate using this birational discretization, then what you see here is an orbit which is spiraling outwards onto the attractor, onto the limit cycle, and here's an orbit which is spiraling inwards onto the limit cycle. So whether you're, maybe if you're only interested in integrable systems, then this is not maybe the right way to go, because there's lots of other good ways of discretizing things. But if you want to preserve some stability properties, then it seems remarkable that these explicit birational maps also preserve stability of these non-integrable vector fields, let's say. Okay, thanks very much for listening.